This is video 10 in our series, Topics in Tensor Analysis. A reminder that the playlist for all the videos is featured at the website, digital-university.org. In this video, we want to conclude our discussions concerning covariant and contravariant components of vectors and tensors, and we're going to be confining ourselves mainly to covariant transformations in this video. Just a reminder of what we've done in the past couple of videos is we had a general curvilinear coordinate system where we have a space curve essentially, u1, that's one coordinate axis, u2, another coordinate axis, and u3, another coordinate axis, where each one of these really are just space curves that are described by some scalar. And in the past video, we gave the example of spherical coordinates with specific equations for these space curves here. Okay, here then we have Cartesian coordinates, and we have a position vector here, and the general formula for the position vector is just this, as we've done in the previous videos. And now we're assuming that we know how to transform from the u-coordinates into the Cartesian coordinates, and likewise we know how to transform from the Cartesian coordinates into the u-coordinate system. And we had that written out in general form in video number 9, so that if we know what the three curvilinear coordinates are, then we can figure out what the Cartesian coordinate x1 is. It's some function of them, and likewise x2 is a different function of these curvilinear coordinates, and x3 is yet still a different function of these curvilinear coordinates. Likewise, if we know the Cartesian coordinates, then the curvilinear ones are different functions of them. u1 we can express as a general function of these Cartesian coordinates, u2 is a different function of them, and u3 is a different function of them. And again, in the last video, we used spherical coordinates to give specific examples of these transformation equations. But that means then that we can write the position vector r, instead of having x1, we can write it then in terms of the curvilinear coordinates u1, u2, and u3. This would be x1, this x2, and this x3. So that we can take the partial derivative of the position vector with respect to u1, or we could take the partial derivative of it with respect to u2, or with respect to u3. So we just have a general formula. The partial of r with respect to ui would just be this. The partial of x1 with respect to ui, the partial of x2 with respect to ui, the partial of x3 with respect to ui, and we can take these partial derivatives because x1, x2, and x3 are functions of u1, u2, and u3. And again, in the previous videos, we went over this in more detail. The point is that when we do that, this gives us a vector that is tangent to a specific u-coordinate axis. For example, if we take the partial of the position vector with respect to u1, that gives us the tangent vector to the u1 coordinate axis. If we take the partial derivative of the position vector with respect to u2, that gives us this other tangent vector that is tangent to the u2 axis at this point P here, that the position vector is pointing towards. And likewise, if we take the partial of r with respect to u3, it gives us e3. And these tangential vectors, we label them with a subscript. even though the axes themselves are labeled with superscripts. Okay, then in video number 9, I believe it was, we did something different. That these curvilinear coordinates, as we said, they're a function of some scalar quantity. And again, we discussed that in more detail in video number 9. But that meant that what we could do is take the gradient of each curvilinear coordinate. And again, if this doesn't seem clear to you, please take a look at video number 9. We went over the mechanics of this in a lot more detail. And when we do that, that gives us a new type of vector. And this vector, we then call it E, and we have a superscript instead of a subscript so that we know it's different than the tangent vector that we formed by taking these partial derivatives. Then what we showed in video number 9 is that if we take the dot product of the tangential vector with the new ones that we created by taking the gradient of each curvilinear coordinate, that they're orthogonal to one another. So we had like this general diagram where here we have coordinates u1, u2, u3, and so forth, and we confine our discussion just simply to the u2 coordinate axis and the u5 coordinate axis. And here are the tangential vectors. E2, this is tangential to the u2 axis at the point P here. And then there is E5, this is tangential to the u5 coordinate axis at this point. And again, we would obtain these, we would have a position vector R, which we didn't draw in here, and then this would be the partial of R with respect to u2. This would be the partial of R with respect to u5. Now, here are the orthogonal ones, E2 and E5, and those we would obtain in general by doing this. And these are orthogonal to these, and that's what we're trying to show in this diagram. Labeled uppercase, so that this is orthogonal to the u5 axis at this point, or be orthogonal to that tangential vector. Likewise, this would be orthogonal to the E2 tangential vector. So that means that if we have a vector A, we can express it by adding up the sum of its components either along the u2 axis and the u5 axis by using their tangential vectors, or we could sum up the components of vector A by taking orthogonal projections along these orthogonal axes, E superscript 2 and E superscript 5. And that would be a different way of writing the vector A. And also we'd have components from the other axes as well. We're not going to write them all out. But this then is the contravariant expression of vector A. This, we said, is going to be the covariant expression of vector A. And we showed in the past video that indeed if you write the vector A like this, and then if we consider a transformation from this system, u1, u2, u3, then we have a different set of curvilinear coordinates, u'1, u'2, u'3, and so forth, where we know how to transform from the primes to the unprimes, and from the unprimes back to the primes. We know how to transform between the two curvilinear coordinate systems. What we showed in the previous videos is that here's vector A in the unprimed system, and if we write it as the sum of the components for these coordinates axes, U5, U6, U4, U1, U2, U3, etc., like this would be the projection of vector A onto U1, this would be the projection of vector A onto U2, and so forth, then that's the contravariant expression for vector A. That's the most basic definition of it. Then what we showed in the previous videos is that if you use the transformation equations, this is how the components of vector A transform. So that if we know a component of vector A here, then we can find out the corresponding component of vector A in the new curvilinear coordinate system, the one that we're calling the primed system. So vector A could be here like this. So really then, this is our most basic definition of contravariant components of a vector. Now, what we want to consider in this video is looking at this situation more closely. So, well, here then we have A being expressed by its components on these new orthogonal vectors that we created. These are orthogonal to the coordinate axis. They're not tangential to them. So let's look at this in more detail. Okay, hopefully this is in focus now. All right. Here then is the definition for EJ with a superscript. We said it's the gradient of some curvilinear coordinate, which we wrote like this. So here the product of UJ with respect to xi, then with respect to x2, and then with respect to x3. Well, we can use the chain rule. The product of UJ, for example, with respect to x1 would be the product of UJ with respect to U prime I, and the product of U prime I with respect to x1. By looking at this chain rule wise, these would just cancel out, and we would have the product of UJ with respect to x1. And again, we know the transformation equations, how to transform from the unprimed to the prime system, so we can take these partial derivatives. Likewise, we can say that the partial of UJ with respect to x2 would be the partial of UJ with respect to UI prime. Then we have the partial of UI prime with respect to x2. Again, just applying the chain rule. And down here, we're going to apply the chain rule one more time. Partial of UJ with respect to x3. That's the partial of UJ with respect to UI prime. Then the partial derivative of UI prime with respect to x3. These cancel, and we have our original expression. So that means that, going back up to here, E with J as a superscript, we said was this, and this, and this, but these here we express now using chain rules. We have this, this, and this that we're going to add together, but we can factor this out. This is common in each one. So what we have then is EJ equals the product of UJ with respect to U prime I, and then we have this one, which is written right here, times the unit vector, times the tangential vector, as we have right here. These tangential vectors are not unit vectors. We've explained that in the previous videos. Then we have the partial of UI prime with respect to x2, and that's times this tangential vector. And then we will have the product of u prime I with respect to x3 times this tangential vector. So by using the chain rule, this equals this, we can rewrite like this. We factor this out. This turns up in each case and we apply the chain rule. Well, if we look at this, the product of ui prime with respect to x1, the product of ui prime with respect to x2, the product of ui prime with respect to x3 multiplied by these tangential vectors, that is the gradient of u prime I, and that we write as e prime I. So what we have is ej is equal to the partial of uj with respect to u prime I times e prime I. Or we could say solve the equation for this and we have e prime I is equal to this. So if, now remember, this is orthogonal to one of the coordinate axes. And if we know what it is in the unprimed system, then we can figure out what it is in the prime system. Okay, so let's just take that a step further. We have this equation. We just derived that. Now, vector A, we can express it in the prime system and in the unprimed system. Here, we have it like this, and this is the one we want to use, then we want to use this one. Here we have, get in better focus, u1, u2, u3, u prime 1, u prime 2, u prime 3, and so forth, and here is vector A. And again, we're just going to consider two of the coordinates, u2 and u5. Well, here now we have these orthogonal vectors. This is orthogonal to the coordinate axis u2. This one is orthogonal to the coordinate axis u5. And we can write A in the unprimed system. We have all the other components too. And we can also write it in the prime system. And that's what we're doing right here. Here we'd be writing A in the prime system, and here we're writing A in the unprimed system. And in each case, it's the same physical quantity. Here would be vector A in the prime system. Here it is in the unprimed system. In each case, it's the same physical quantity, so these have to equal each other. But E superscript j is equal to this quantity. So we can write this, we have E sub j. Then we have, substituting for Ej, we have this. Well, let's compare then this equals this. We can cancel these out, and we have A prime I equals this derivative times Aj. So what that means is that if we know a component of our vector A on one of these orthogonal axes, and these components now we write with lower subscripts, and this one is written incorrectly. This should be down here, like this. The orthogonal axes are labeled with superscripts. The components along them are written with subscripts. So what we're saying is that if we know a component of vector A on one of these orthogonal axes, we want to know, well, what would it be on the prime system over here? Here's the expression for it. If we know the component of A in the unprimed system, here it is in the prime system. And we look at this, And we see we're taking these partial derivatives and we're summing over this common index. And that right there is the hallmark of what we said in video number 2 when we are taking covariant transformations. They have that exact property. So what we're trying to show in this video is that, looking for the correct diagram here, when we have a vector and we express it in terms of its components along axes that are perpendicular to our coordinate axis using this expression, then when we transform from one coordinate system to another coordinate system, then that transforms exactly according to the pattern of a covariant vector. So really, this is the most basic definition then of a covariant vector. And if you look now in, I think it's video number 5, we generalize from covariant vectors to covariant tensors and contravariant vectors to contravariant tensors. You might find that worth looking at again. But that concludes this video. What we wanted to show is that this is the most basic definition then of what covariant components are. Likewise, when we're expressing a vector in terms of its components along the coordinate axis using the tangential vectors, that's the most basic definition, the fundamental definition of the contravariant components of the vector. Okay, come back, join us in the next video, and we can start talking about raising and lowering operations, and then finally discuss what a metric tensor is.